These are the notes on modeling gas relationships. We're going to look at the relationships between pressure, volume, and temperature today. As a reminder, these are the variables that we have for gases. The amount of gas that we have, or the moles, is a variable. We're not going to focus on what if that's changing today or that's relationship with any of our other three variables. We are going to focus on volume, which is the size of the container holding the gas, pressure, which is the outward push of gas molecules on their container, and temperature, the speed or kinetic energy of the gas molecules. So those are the three variables we're going to look at, the relationships between volume, pressure, and temperature. And we're going to also look at modeling the relationships of those variables. There are two types of relationships, and we're going to be looking at just two variables at a time to look at those relationships. We are going to see direct relationships, which you can see in graph A. And that is when one variable changes, the other variable is going to change in the same way. So example, as height increases, weight increases, or as height decreases, weight decreases. Could be an example of a direct relationship. An indirect relationship, that's what we see in graph B. When one variable changes, the other variable changes in the opposite way. So example would be as spending increases, the amount of money you have decreases. And vice versa. All right, so our first gas law we're going to look at is Boyle's law, which is the pressure-volume relationship. And with these, we have a couple of videos that we're going to look at. We're going to look at identifying what variables are changing. So our three variables at the top are pressure, temperature, and volume. And then we have a little video here. The full videos, or the videos, are linked within with the notes. And so you can always go and look at more of these videos a little bit more if you want. We're going to just watch a little part of it and then kind of discuss what's changing, what isn't changing, and go from there.
As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
Okay, I think we usually intend to play that on mute, and I forgot. So it did give a little bit away. So, and there's a little at the top, a vacuum is a space that's empty of matter. And so with this, putting it in a vacuum chamber. So what was changing? Well, as air was removed from that vacuum chamber, the pressure was changing on the shaving cream. So pressure was changing. They said they were taking any of the excess air out of that chamber. So pressure was changing. And then what else did we see changing? Well, I saw that shaving cream get larger. And he'd said there's gas inside of that shaving cream. So that volume was changing as well. We didn't have any indication that temperature was changing. So that temperature stayed the same. And so we're just going to look at first our pressure-volume relationship with that. And so how are those changing? So as pressure is decreasing, as we look at what we observed, as pressure is decreasing, what was happening to the volume? Well, I saw that volume increasing. Go ahead and you can always go back and watch the video again if you need. But this is the relationship of Boyle's law, which is the pressure-volume relationship. And so Boyle's law states that as the volume of a gas is decreased, the amount of pressure is increased at a constant temperature. So this requires temperature to stay constant. And that means that volume and pressure are inversely proportional. So they are going to behave opposite. That means that if pressure increases, volume is going to decrease. That also means that if pressure decreases, volume is going to increase. So they're going to behave opposite. And with those, we could also switch them. We could say if volume decreases, pressure increases. So how those are typed out on there is just so that, because we're just comparing that pressure and volume. And so again, the image on the right shows us that pulling up increases the volume and decreases the pressure. And so those particles have more space to move around, which means they're not going to collide with the container as much. But when we push down, it decreases the volume and increases the pressure, because then those molecules have less space, so they're going to collide more. So examples of Boyle's law during respiration, our lungs make use of Boyle's law. So when inhaling, the lungs are filled with air, therefore they expand, the volume increases, and so the pressure, the gas pressure is going to decrease, and then vice versa. Another example is a hand bicycle pump. And so when the handle of the pump is pushed down, you're decreasing the amount of volume within the pump. And with less volume, the pressure inside the pump increases momentarily, and then the gas inside is forced into the air tire. So those are two examples of where we see Boyle's law and that pressure-volume relationship. Next is Charles' law, and this is going to look at the volume-temperature relationship. So we're going to watch another video. Consider the variables, pressure, temperature, and volume, what things are changing and what things are staying the same. We're going to look at liquid nitrogen on a balloon.
It is colder than any place on Earth, but not as cold as space. This balloon is filled with air, and we're going to pour liquid nitrogen on it and see what happens. Now, a lot of people think that the air has escaped the balloon, but I can prove to you that the air is still in there. As the balloon warms up, it reinflates. So what do we think is happening? Well, the liquid nitrogen...
All right, so what is changing here? So using that liquid nitrogen, that is going to be cold, so we see that change in temperature. And what else did so she told us that was cold, so the temperature was going down. And then what else changed? Well, volume, we want to look at the size of the container that that gas is in. The size of that volume also changed. Pressure did not change throughout that. And so when we're looking at Charles' law, we're looking at the temperature-volume relationship. And how are these variables changing? As temperature is decreasing, what happened to our volume? I saw the balloon get smaller, so then the volume is decreasing. And that is Charles' law, which is the temperature-volume relationship. So Charles' law states that as the temperature of a gas is increased, the volume is also going to increase when pressure is kept constant. So we're keeping pressure the same, the collisions within the container are going to stay the same. And because those change in the same way, if one increases, the other increases, and if one decreases, the other decreases, that means that these are a directly proportional relationship. All right, and there's an image off to the right for us. Feel free to read kind of below. It kind of reiterates what I said. Some examples of Charles' law. Yeast is used in baking. And so with yeast, they release carbon dioxide bubbles. The expansion of those bubbles is going to increase the volume. And so this is why if you let something with yeast in it sit out over time, that's why it is going to rise. If you use a proving drawer, or even when you put things into the oven, then those are going to continue to rise, which means that as temperature is increasing, volume is doing the same thing, increasing as well. Another example is if you play ping pong, you might have come across dented ping pong balls. In order to change that, you could put a dented ping pong ball, let it float on hot water. You don't want it too hot to melt the ball. But then if it's on hot water, the air inside the ball will heat up as well. And then it will then increase that volume because it will need a certain amount of volume to increase the space that the air can occupy. All right, our last of these relationships is the pressure-temperature relationship. All right, again, our three variables. We've got pressure, temperature, volume, considering what's changing and what isn't changing. All right, so with this one, what's changing? So that candle inside the canister, we've got temperature changing. That candle is going to heat up the gas that's inside of the jar. And then what's happening as a result? There's an increase of pressure inside, which then allows that liquid to be sucked up from the plate into that upside down jar. So what's changing? That volume, the canister is fixed, or the jar has a fixed volume, so that volume is not changing in this case. And so how are those variables changing? Well, as temperature increased because of the heat of the candle, the pressure is increasing. And so with this one, with Gay-Lussac's law, it states that as temperature of an amount of gas increases, its pressure will increase at a constant volume. And so this again is with the same amount of gas, and temperature and pressure then are directly proportional. And so if temperature increases, pressure increases, and vice versa. If pressure increases, temperature would increase. And then if temperature decreases, pressure decreases as well. And looking at our picture over here, as the temperature increases, then those particles are going to be moving around faster. And that means if those are moving around faster in a fixed amount of space, they're going to run into each other more. So then we have more collisions with the surface of the container in order to maintain that volume. Some examples. That pressure cooker example is here as well, and you saw it on our first set of notes when we were looking at modeling. Because a pressure cooker has a fixed volume, then as the temperature, that liquid water is going to change to gas. That as that gas heats up, it's going to then have a higher pressure inside, and that allows for quick cooking. Also, if you are a driver, maybe this has applied to you. On hot summer days, the inflated tires of a vehicle may burst. The inflated tires are under high pressure. So when the temperature of air rises, the pressure of the gas in the tubes is going to increase. And tires can fracture if they get too hot. Same thing with this is that opposite. When it gets too cold, if we live in Minnesota, and so as the temperature goes down as we get into winter, you often have to go and add more air into your tires because as temperature goes down, then the pressure is going down as well. And so that is because of our gas behaviors. All right, I'm going to go ahead and do the particle diagrams on a different video. So hop over to that video, and